Hey there, friends. This is a quick video in response to some questions I had about the notion of partial fractions. The question was a little bit more specific than that, but I think partial fractions is an integration technique that's going to come up often enough that maybe I should go ahead and look at the fuller sort of question. So in general, the problem you're running into with partial fractions is that you're trying to integrate something that has a polynomial on the top and a polynomial on the bottom. So first thing is, if the degree of the top is higher or the same or higher than the bottom, do long division. That's the first step, okay? So we're going to presume that we're dealing with a rational function that has a degree of the numerator is smaller than the degree of the denominator. That's the first thing to do. Now, when that happens, you're going to need to factor your denominator and see what kinds of terms you have. When you factor that denominator, it will factor into linear and quadratic terms. The quadratics hopefully would factor further, but sometimes you get irreducible quadratics like, say, x squared plus 1 or something like that. So what we're going to look at is how to handle each of several situations. All right. So I'm going to share my screen here, and I will have to tell my iPad what it's sharing. Oh, nope, it doesn't have to be told. It just has to turn damned iTunes off. All right, so you can see the problem that we're working on here, and the real thing that we have to do with it is not so much the calculus, but rather doing some algebra. This is really 1 over x squared minus 5x plus 6, which I don't know why I would bother to not just factor that as I go along. So I'm just going to go ahead and factor it. Oh, come on, pencil there, into x minus 2 times x minus 3. Okay, so if you have distinct linear factors, nothing can be repeated factors. Okay, no quadratics. So if you have distinct linear factors, you set it up a over the first factor and b over the second factor. Okay, so I'm going to show you first a technique that always works. It always works, but sometimes it's difficult. Okay, and then I'll show you an easier way that doesn't always work, and we'll talk about the things that might come up. So the thing that we're going to do with it set up like that is to cross multiply. So essentially I'm taking both sides and multiplying by the x minus 2, x minus 3. Okay, and of course here on the left-hand side, it just cancels out and you've got 1. On the right-hand side, you have to distribute, and when you distribute in here with the a, the x minus 2's will cancel. You have a times x minus 3. You have b times the x minus 2, because it will cancel the other part. Okay, so this method that always works is to go ahead and distribute, and then to collect together the coefficients of each variable there. So, sorry, said that the wrong way. The coefficients of each power of the independent variable, the x. And I wrote the wrong thing there. Let me fix that. Minus 3a minus 2b. Okay. So, if you look over here at the left-hand side, it does not have an x term. So you have to think of it as 0 times x. We are going to do what's called equating coefficients. Because the two functions on the two sides of the equation have to be the same function, that means the a plus b needs to be equal to 0. And the minus 3a minus 2b needs to be equal to 1. Okay? And now we're going to go ahead and solve that. All right. Quick comment about this. Everybody who has been in high school recently is totally convinced the only way to ever do anything is substitution. Fine, you can do substitution and you'll be finished with this problem faster. But there's a reason to do it the way I'm doing it. So I'm going to take and multiply this equation here by 2, and I'll put it down below and have 2a plus 2b equals 0. Everybody, I hope, sees why I multiplied by 2. Those cancel out. I have minus a is equal to 1, so a equals minus 1. Now, because a plus b had to be equal to 0, b has to be plus 1, all right? Now, once I've got that, I can go back into my integration, write integral of minus 1 over x minus 2 plus 1 over x minus 3 dx. We're doing a u substitution, but it's an easy u substitution. Negative log absolute value x minus 2 plus log absolute value x minus 3. What goes at the end? Plus c. Got to remember that. And if you would like to, you can then turn that into log of the absolute value of x minus 3 divided by x minus 2. Since the minus 1 out in front of the log of x minus 2 could be interpreted as the minus 1 power. All right, so that gets us our answer here. But you're saying, but Ben, you promised to show me something easy. Yes, totally did. So we have 1 over x minus 2, x minus 3 equals a over x minus 2 plus b over x minus 3, right? That was the equation we were working with before. Now, there's a little bit of a problem in that I normally do this on a chalkboard. So when I do this, it's maybe not going to have quite the same visual, but I'm doing something called the Heaviside cover-up method. That's named after a mathematician named John Heaviside. So it's, yeah. So if we look over here on the right-hand side to this bit that has the x minus 2 there, I'm going to come over here to the left-hand side and cover up the x minus 2, right? Now, what is a bad value to have plugged in for x in that x minus 2? 2, right? Because then you would divide by 0. Now that we've covered it up and we totally can't see it, we are going to plug in our x minus, our value of 2 to, we're going to plug in our value of 2 for x. And so when you do that, you'll have 1 over 2 minus 3 is minus 1. And that is going to be your value of a. Okay. And now, unfortunately, I don't have a way to get the cover up off there without doing this. So we got a equals negative 1 by plugging x equals 2. Then we're going to do the same thing again, but a bad value to plug in here for x would be 3. So we cover up that factor here. and we plug in and do the calculation in our heads, and we will find out that we have 1 over 1. So B has to be 1 over 1 by plugging in x equals 3. Okay, so that is referred to as the Heaviside cover-up method. So another route to go that's also very easy is once you have it in the shape here, okay, rather than thinking about bad values to plug in, think about values to plug in that will make something go away. So if I plug in x equals 3 here, it will turn the equation into 1 equals a times 0 plus b times 1, and that tells me b equals 1. If I were plugging in x equals 2 here, then I would plug it in and get 1 equals a times minus 1 plus b times 0, so a equals -1. Okay, really you're doing the same thing as the Heaviside cover-up method there, but you're thinking about zeroing things out. Okay, so that is our example of what to do when you have distinct linear factors. So now we have to go in and say, what if I don't have exactly that? What if instead the thing I was working on had repeated factors? Okay, so I'm going to write something down here. I guess I might as well be sharing screen because you don't need to see my beautiful face out there, right? So this one has x cubed plus 2x squared plus x. So that's what we're integrating this time, okay? And so when we do that, we know that what we're really dealing with is the algebra, and we have to factor that bottom, and so it'll have an x and an x plus 1 squared, right? So the distinct factor and there of just x, we'll put an a over x. Now, for the repeated factors, you have to build your way up. You cannot just skip to the end. You have to have a b over x plus 1, and then a c over x plus 1, the quantity squared. Okay? So, do the same thing as before of multiplying both sides by x and x plus 1 squared. And the left-hand side has cancellation. And you've got this. And then here on the right-hand side, you have to think about multiply it through this piece, and the x would cancel, and you'd have a times x plus 1 squared plus and b times the x would not cancel, but one of the x plus 1s would, and then plus c times x. Okay. Now, you can either go through the method of equating coefficients, or you can go through the method of substituting something in. I would like to go ahead and substitute something in here in order to point out a difficulty which will arise. All right. So substituting in x equals -1 is going to make a factor be 0 there. On your left-hand side, then, you are going to see that you'd have to get +5 and negative 20. So that means negative 15 so far, and then plus 6. So you end up with a negative 9 equals A times 0, B times negative 1 times 0, but C times negative 1. And so since these terms dropped out, you can immediately see that C equals 9. Okay? And then we're going to go back and say, plugging in x equals 0, because that's going to make this piece disappear. X equals 0 is awesome. If there's no reason otherwise to plug in x equals 0, sometimes you just plug in x equals 0 because everything's easy. It makes the left-hand side be 6. And then the right-hand side, you've got A times 1 squared, but that's just 1, plus B times 0 times 1, and plus C times 0. So those terms fall out, and we know that A has to be equal to 6. Okay? Then, to get B, none of the things that we've plugged in before actually are valid, because if you plug in x equals 0 or x equals -1, B drops out. So you have to just pick some value at random if you want to continue this. But be smart. Always choose values that are close to 0. So we chose x equals -1 before. Let's choose x equals +1. Okay? So if there were other things to have drop out, we would choose those. But if there's not, then we just try x equals 1. And of course, on the left-hand side, you end up with 31. And then on the right-hand side, you have an A times 1 plus 1 is 2. 2 squared is 4. And then B times, and you've got a 1, and 1 plus 1 is 2. And plus C times the 1. Okay? Now, fortunately, we know some of these values. So here you've got 31 equals 4 times A, but A was 6, so that's 24, plus 2 times B, we don't know B, that's what we're solving for, plus C is 9. So that means that we have 2B plus 33 equals 31, 2B equals -2, B equals -1. All right? Now we've got our A and B and C. It was a lot of work, I feel like, but we go back to the integral, and we have to look back up there and see what the integral looked like. So you see the A and B and C. So we're going to have this integral of 6 over x plus -1 over x plus 1 plus 9 over x plus 1 quantity squared, and then all dx, right? So then the actual integration is almost trivial, right? Integrating 6 over x, you'll have 6 ln absolute value of x minus the integral of 1 over x plus 1 will be log absolute value of x plus 1, and then plus 9 times. Now, you have to do a u sub for this, but the u is just x plus 1, so the du is dx. And so it's really as though you were integrating 9u to the -2. So you will end up with an x plus 1 to the -1 power, and then you'll have to divide by that -1, so put that out front and have a plus c. So this becomes log absolute x to the 6th over x plus 1 minus 9 over x plus 1 plus c. And there we got that. All right. So if you've got something with linear factors, everything turns out pretty nicely. So then we have to look at a quick example of something that has irreducible quadratics in it. It tends to be a little bit of a pain to do, okay? But we'll work through an example that's not too terrible. So the integral here has up on top 2x cubed minus 4x plus 8. And on the bottom has x minus 1, x squared plus 4 dx. All right. So we're saying 2x cubed minus 4x plus 8, x minus 1, x squared plus 4. Okay. So the x squared plus 4 will not factor down any further. And we'll have an a over x and a b over x minus 1. And then over the irreducible quadratic, not factorable, we'll have cx plus d over the x squared plus 4. Okay? So then you'll multiply denominators like before. You'll have 2x cubed minus 4x plus 8. You'll have a times x minus 1, x squared plus 4, plus b times the x and the x squared plus 4, plus, sorry about this, cx plus d times the x and the x minus 1. See what I mean about it is a little bit miserable? So x equals 1 is a value that'll be convenient to plug in, and x equals 0 is a value that's going to be convenient to plug in. So I'll start with the x equals 1, right? So over here on the left-hand side, plugging in x equals 1, you've got, let's see, 2 minus 4 plus 8. So that would mean that you end up with 6 is equal to. Now, all the stuff that has an x minus 1 factor drops out. So you end up with just the b times 1 times, let's see, 5. So b is 1.2. Bang, done. X equals 0 is going to make all the things with just an x come out. And so 8 equals, because the left-hand side is easy to do, a times minus 1 times 4. So that says that our a is going to be equal to minus 2. Boom, done. Then we're out. We're out of the options that make it easy. So if you remember my advice from before, choose stuff that's close to 0. So when you plug in x equals negative 1 there, then you end up with a negative 2 plus 4. So that's plus 2 so far onto the 8. So you get a 10 equals a times negative 2 times 5 plus b times negative 1 times 5 plus negative c plus d times negative 1 times negative 2. So simplify that where we can. Fortunately, we know a value for a, so this part here would turn into, let's see, 20. We know a value for b, so when you multiply that there, you will get negative 6. And then we'll simplify this stuff here by multiplying out and have minus 2c and plus 2d. So minus 2c plus 2d plus 14 equals 10. If I divide that out, I have c minus d minus 7 equals minus 5. I guess I should have added the stuff first, but I end up with c minus d equals a positive 2. Ugh. X equals. So for our last choice here, I'm going to choose positive 2. If you wanted to choose some other value, have a field day, but I don't want to have to do the awful arithmetic. So for x equals positive 2, let's see, I would have 2 times 8 is 16. And then minus 2 times 4, so minus 8, and then I lost my place, plus 8. Oh, so yeah, so it's just 16 equals, and like before, the a times 2 minus 1 is 1, and then 2 squared plus 4 is 8, plus b times 2 and 8 plus 2c plus d and times 2 and times 1. So 16 equals 8a, but a was equal to negative 2, so it's negative 16 plus 16b, but b was 1.2. Oh, crap. So I hate to disillusion you, but I'm going to actually have to grab a calculator to say 16 times 1.2 is 19.2. And then plus 4c plus 2d. So simplifying, 4c plus 2d plus 3.2 equals 16. 2c plus d is equal to, let's see, 8 minus 1.6 is 6.4. So if I take this up here and add those together, I'll get rid of my d's. I'll have 3c is equal to 8.4, so c is equal to 2.8. And since c minus d needs to be 2, the d must be 0.8. Now I've got all my stuff. And I have to scroll all the way back up here to see what the hell was it I was working on. So a over x, b over x minus 1. So a was negative 2. B was 1.2 plus 2.8 x plus 0.8 divided by x squared plus 4 dx. So we are having to integrate minus 2 over x plus 1.2 over x minus 1 plus, because that x squared plus 4, for a u substitution of x squared plus 4 will get you factors of x, we'll say 1.4 times the 2x over x squared plus 4. So we're going to do u sub essentially in our heads. Sorry. And a 0.8 times the 1 over x squared plus 4, which hopefully you remember goes to an arctangent type thing. So negative 2 log absolute value of x plus 1.2 log absolute value of x minus 1 plus 1.4 log absolute value of x squared plus 4. course, x squared plus 4 is always positive, so that's not a problem. Plus 0.8 times, oh, how's this go? It's x squared plus a squared. So it's 1 over the a is 2, inverse tangent of x over 2, and then plus c. If you would like to collect all of your logarithms together, you can have the log of the absolute value, good Lord, of x minus 1 to the 1.2 power, and then the x squared plus 4 to the 1.4 power divided by the x squared, okay? And then plus 0.4 inverse tangent x over 2 plus c. Oh, that was miserable, you know, but we came down to an answer. And sometimes the most important thing is that you can get an answer, not that it's nice. So, all right, so hopefully that will help you all out with partial fraction stuff. I'm going to go ahead and stop the recording there.